In this video, I'm going to show you how to differentiate an equation which is not explicitly solved for y. We're going to use implicit differentiation, which just involves taking the derivative with respect to x of both sides. Then we'll use the chain rule to get some dy dx's in the expression, and then we can solve for those. But the first step is to differentiate. So we'll take d over dx of both sides of the equation. And we can go ahead and split up this derivative over the sum. So this is d over dx of x to the fourth plus d over dx of y squared. And the derivative of 5 we know is just 0, because derivative of any constant is 0. Okay, so let's continue computing this. Derivative of x to the fourth, from the power rule, we know that's 4x to the third. And then derivative with respect to x of y squared, how do we do that? Well, there's no x in there, but y isn't a constant, so what do we do? So why don't we just leave it as d over dx of y squared for now, and then we'll take care of that in the next step. And the next step is to apply the chain rule. So for the chain rule, we're going to leave this 4x third term alone. We're going to focus in on this d over dx of y squared term. And the way we're going to use the chain rule to find the derivative of this term is we're going to start out by taking the derivative with respect to y of y squared. And then the chain rule says that we can do that provided we multiply it by dy dx at the end. It's like the dy's cancel to yield our original d over dx. So now that we have this expressed as d over dy, we can go ahead and compute that derivative. So this is 4x to the third plus d over dy of y squared. Well, now the variables match up, and we can just use the power rule, 2y, and then we've got our dy over dx term. That equals 0. Great. So now it just remains to solve for this dy over dx term. We can do that using just regular algebra. So we'll go ahead and start by subtracting off this 4x to the third, and we get 2y dy dx equals negative 4x to the third. And then we can divide by that 2y, and we get dy dx equals negative 4x to the third over 2y. And we'll just simplify this a little bit, and we get dy over dx equals negative 2x to the third over y. And that is our final solution. That's the derivative of y with respect to x given this equation. Let's do another example. This example is a little bit trickier because here we have a product of terms, and we also have y on both sides of the equation. But the steps to finding dy dx using implicit differentiation are still the same. We're going to start off by differentiating both sides with respect to x. So we'll take d over dx of both sides. And again, this derivative will distribute over the addition. So we've got d over dx of y root x plus d over dx of the other term, sine x. That is equal to d over dx of x and plus d over dx of 2y. Okay, so now we can go ahead and start computing these derivatives. This first derivative is going to require the use of the product rule because we've got a product of terms here. So we take the derivative of the first term, so d over dx of y, times the second term, root x, plus the first term, y, times the derivative of the second term. And we can go ahead and compute some of these derivatives. So derivative of sine, that's just cosine. That's equal to derivative of x is just 1. And then we'll keep this derivative as just d over dx of 2y because that contains a y, and we're going to need to use the chain rule. But let's not worry about that just yet. Let's continue simplifying this as much as we can. Looking at this term right here, d over dx of root x, we can find that derivative. So let's just write everything again and compute that derivative. So that derivative of root x is just 1 over 2 root x. And then we've got all the other stuff that we had in the previous line. All right, great. So now the only derivatives we have left are those which have y terms in them, and we can't take those derivatives just yet because it's d over dx of a y term. So how do we reconcile that? Well, it's the same way as before. We're going to use the chain rule. And remember that the chain rule says that we can take the derivative with respect to y, can change that x to a y as long as we multiply by dy dx at the end, so that the dy's cancel out and we've just got our d over dx that we originally had. So we're going to apply the chain rule to those two derivatives and write down all the other stuff in between. So let's condense this. This is y over 2 root x plus cos x equals 1 plus, this is derivative with respect to y of 2y times dy dx. And then we can go ahead and take these derivatives now that the variables match up. So d over dy of y, that's just 1. So 1 dy dx root x plus y over 2 root x plus cos x equals 1 plus d over dy of 2y, that's just 2, and then we've got our dy over dx at the end. And now that we've taken these derivatives, we just need to solve for the derivative. So we're looking at this and this. We want to group up these dy dx terms and just get them on one side of the equation by themselves. So we're going to head and we'll keep this term on its side of the expression right now. So dy over dx root x, and then we'll subtract off that 2 dy dx term. So minus 2 dy dx. We'll write that 2 in front instead of in the numerator. So this term minus this term equals, we'll move these two terms to the other side. So that's equal to 1 minus this term, y over 2 root x, then minus that term, minus cos x. And now we can go ahead and factor out a dy dx. So we've got dy dx root x minus 2 equals that same right-hand side, 1 minus y over 2 root x minus cos x. And to finish it off, we can divide by this root x minus 2 and just get dy dx equals that same right-hand side, 1 minus y over 2 root x minus cos x all over root x minus 2. And there we go. That's our derivative. The whole process was a little bit more complex, but it followed the same general steps: differentiate, then chain rule, and then you solve. For our final example, we're going to tackle a similar problem. We've got a product and y on both sides of the equation, but the difference is that we want to find the derivative at a particular point, 2, 2. But the process is still going to be the same. We're going to start off by differentiating. We'll take d over dx of both sides of the equation and go ahead and simplify here. So we can use the product rule to take the derivative of this product. That's just the derivative of the first term, x minus 1 to the fourth. Derivative of that is just 4 times x minus 1 to the third, and then times the second term, y squared, plus the first term, x minus 1 to the fourth, times the derivative of the second term, y squared, and that's equal to, we'll just distribute this derivative over the sum. So d over dx of y, we'll do that once we use the chain rule. And then d over dx of 2 is just 0 because 2 is a constant. Okay, so now we're ready to go ahead and use the chain rule. We've got this term and this term, which are both derivatives with respect to x, but we've got y inside of the argument of the derivative. So we'll go ahead and rewrite what we had before. We had 4 times x minus 1 to the third y squared plus x minus 1 to the fourth. But now that's d over dx. We change that to a d over dy, so we can actually take the derivative of the inside. But we have to multiply it by dy over dx so that these dy's cancel and it's equivalent to what we had before. So we'll do that to this side also. The x changes to d over dy of y, and then we multiply by dy dx. Then we forget about that 0. Okay, so now we're good to go ahead and compute these derivatives with respect to y. So let's write down what we had before again. So this is 4x minus 1 to the third y squared plus x minus 1 to the fourth. Derivative of y squared with respect to y, we just use the power rule. So that's just 2y. Then we've got our dy for dx. That's equal to derivative of y with respect to y is just 1. And we've got our dy over dx. Okay, so now it remains to solve for the derivative and evaluate it at that point. And we could solve for the derivative first, like usual, and then just plug in 2 for x and y. But here it's actually a lot easier to plug in this point to substitute it for x and y in this equation, because then we just have concrete numbers while we're solving for dy dx, and it simplifies a whole lot. So let's do that first. Let's go ahead and substitute this point 2 for x and y. So we got 2 minus 1 to the third times 2 squared plus 2 minus 1 to the fourth times 2 dy dx equals just dy dx. And we can go ahead and compute these. So this is 4 times 2 minus 1 to the third is just 1 to the third, which is just 1. And 2 squared is 4, so it's just 4 times 4, that's 16. And then 2 minus 1 is 1 to the fourth, it's still just 1, times 2 times dy, so we've got plus 4 dy dx, and that's equal to dy dx. So by substituting, we reduced this mess of variables equation down to this very easy to solve equation. And we'll go ahead and solve it here. So we'll go ahead and subtract this dy dx to this side. So we get 3 dy dx. And we'll move that 16 over. We'll subtract 16. So equals negative 16. And then we just need to divide by 3. So dy dx equals negative 16 over 3. And there's our solution. And just remember, that's at the point 2. That's the derivative evaluated at a specific point. In general, the derivative is an expression of x and y, but remember, we substituted this point in, and that's why we've got a concrete number here. In the future, we'll also use implicit differentiation to do more interesting things, such as calculating tangents and normals to curves.